Hello everyone, I'm Thanh Trần. I'm a PhD student at Miss Sweden University. Today I would like to present my research about real failure detection based on sound using AI. A machine failure detection system is a system for automatically detecting and diagnosing a various types of machine failure. It is a very interesting process in industrial application. A drilling machine is a kind of rotating cutting machine that is used widely in factories to drill holes in material such as metal, wood, and plastic. The timely detection of problematic drill bits is essential to prevent damage to materials due to drilling failure. Because the cutting of a drill makes sounds, skilled technicians can distinguish the sound of a drill that is not working properly and immediately stop production so that the drill can be repaired. Our main purpose is to build a system to detect the failure in the drilling machine as shown in this figure. So we can put a microphone near the machine to record the machine sound and automatically put an alarm when any drill bit is broken. The content includes three sections. Section 1 is the introduction. Section 2 is the proper measures. Section 3 is the conclusion. So the figure on the left side shows a drill machine at Vamet AB when it is idle and when it is active. The figure on the right side shows a normal drill bit and a damaged drill bit. Vamet AB is currently operating multiple drilling machines to drill thousands of small holes in metal plates as shown in this figure. Each drill machine consists of 90 or 120 drill bits. A technician usually turns off the drill machine every 10 minutes to check its status. Any drill bits that are damaged must be replaced to ensure that all holes are drilled on the surface of the metal plate as intended. Stopping the production line is time-consuming and labor-intensive. Therefore, an automated system that detects broken drill bits is essential in production to reduce production and labor costs. Most machine failure detection systems use vibration. However, for the work environment AB, each drill machine includes 90 or 120 drill bits. If we use vibration for each drill bit, we may need one sensor. It is expensive and complicated to mount the vibration of 90 or 120 sensors. Moreover, the collection and labeling of sound can be a time-consuming and expensive process for a company since the error does not happen quite often in the factory. So I focus on solving the research question to build a machine failure detection system based on machine sound, especially on a small dataset. My solution is using data augmentation technique to transform datasets. Additionally, in order to create variations that are representative of what a deep learning model might see in reality, data augmentation technique enable deep learning models to be more robust. The dataset we use includes two classes, anomaly sound and normal sound. Each class has 67 sounds. I visualize the signal of two sounds in time domain here. Our proposed procedure is shown in this figure. We use VIE to generate more drilling sound from the original drilling sound as a data augmentation strategy. The original sound will combine with the generated sound from VAE to form the augmented dataset. Then a low-pass filter with a pass band of 22,000 and a high-pass filter will apply to this dataset as part of the pre-processing procedure. After pre-processing, the sound were converted into MEL spectrogram and classified using pre-trained deep learning model. Firstly, we create a VAE to generate new drilling sound from the sound in the original dataset. A VAE is an architecture that belongs to the field of probabilistic graphical and variational Bayesian. A VAE is composed of an encoder and a decoder. It first takes an input sound and creates a two-dimensional vector, mean and variance, from a random variable. A sample encoding is obtained from this vector and passed to the decoder. The decoder decodes this one-dimensional vector and recreates the original sound. The decoder is capable of learning from all nearby points on the same latent space because encodings are generated from distribution with the same mean and variance as inputs. The divergence between probability distribution were controlled by Kuhnbeck-Leibler divergence. Kuhnbeck-Leibler divergence is minimized by optimizing mean and variance to closely resemble that of a target mean and variance. The detailed architecture is shown in this image. It includes encoder part and decoder part. The encoder includes 4 one-dimensional convolutional layers with 4 redness encoder blocks. The input of the encoder are 1,999 length vectors corresponding to 1,999 sample points of each sound in the dataset. Redness encoder block include 2 one-dimensional convolutional layers and 2 instance normalization layers. A channel's features are normalized by instance normalization. The decoder includes 4 redness decoder blocks with 4 one-dimensional convolutional transpose. The input shape of the decoder is a latent dimension vector from encoder. Redness decoder block includes 2 one-dimensional convolutional layers and 2 batch normalization layers. A transpose convolutional layer has the opposite transformation as a normal convolutional layer. This is achieved by transforming the latent space that has the shape of the output of a convolution into something that has the shape of its input while maintaining a connectivity pattern that is compatible with the convolution. The original sound will combine with the generated sound from VAE to form the augmented dataset. Then a low-pass filter with a pass band of 22,000 Hz and a high-pass filter with a pass band of 1,000 Hz will apply to this dataset. After pre-processing, the sound was converted into MEL spectrogram. So what is a MEL spectrogram? MEL spectrogram is combined of MEL scale and spectrogram. And spectrogram, this is a transformation of the y-axis and the color of the results in the Fourier transform to log scale. And the MEL scale is a perceptual scale of pitches judged by listener to be equal in distance from one another. And the MEL comes from the word melody to indicate that the scales is based on pitch comparisons. MEL spectrogram better suited for applications that need to model human hearing perception and suited for use in audio classification application. Then the last step, we train a classification model. We filter several common pre-trained models for classification. And this table on the left side compares the accuracy of different models. AlexNet achieved the high-gate accuracy of 94.12% on our dataset. The confusion magic for the augmented dataset of AlexNet is shown on the right side. It is obvious that the accuracy of AlexNet when trained on augmented dataset is 94%, that is higher than trained on the original dataset that reached only 87.5%. Yeah. So in conclusion, to answer the research question about building a machine failure detection system using a small sound dataset, we use VAE to synthesize 96 new drilling sounds from 134 original drilling sounds. Then we combine the new sound and original sound to create the augmented sound dataset. Then we train a pre-trained AlexNet to classify male spectrogram of sound. Then the overall accuracy of classification reached 94.12% when classifying normal and anomaly sounds using AlexNet. Thank you very much for your attention.